So good afternoon everybody. Let me first start thanking the organizers for inviting me over here to giving me an opportunity in this magnificent event, actually very large event. And so today I will be talking about complex magnetism in strongly correlated quasi 2D systems. I will try to cover these two systems. One is this Fe4GeTe2 and another is transition metal hydroxide series. I will see that how much I can cover. So in this so we usually follow one kind of mechanism. So the key theme of that mechanism is that basically we study the interplay of strong correlation and then dynamical magnetism, chiral spin structure, and also the optical, vibrational and core level spectral properties. For strong correlation, we use usually DFT plus DMFT, where depending upon whether the system is metallic or weakly correlated, or is it insulating or semiconductor, we use different kinds of solvers for the DMFT, and then for dynamical magnetism we calculate the inter-site exchange interaction and construction of that LLG equation, and then definitely we will be doing the atomistic and micromagnetic spin dynamical simulations for exploring the chiral spin textures and optical, vibrational, core level spectral properties. Those will be modeled by doing that phonon calculation and also DFT plus DMFT plus MLFT calculation. And this quasi 2D system, as I have specified, these two systems we will be doing, and here are some of our recent works. And some basic mechanism of DFT plus DMFT. So we usually take that the impurity the levels are my correlated levels, and those are actually embedded within the bath electrons, and there is an exchange between this impurity and the bath. And from the converse DFT we usually calculate the lattice Green's function, and then from there the bath Green's function, and via this inverse Dyson equation and DMFT solver we calculate the self energy, which is calculated as a function of the Matsubara frequency, which has a temperature dependence. And usually, as I have told, that depending upon whether the system is weakly correlated or strongly correlated, and whether the system is having a metallic character or whether it is a non-metallic insulating or semiconducting character, we choose our solver. One of the solver for the metallic system is a perturbative solver, which is SPTF solver, which is spin polarized T-matrix fluctuation exchange solver, where we that it is actually a spin polarized that treats the spin up and spin down electrons explicitly, and then the T-matrix is actually calculated by a ladder diagram, where the electron scatterings are calculated by a pair of these electrons which are interacting repeatedly via this U, and then these G are the perturbative, these are the propagators, and you calculate also the fluctuation exchange, which is which actually gives the effect of the spin and the charge fluctuation. So total that self energy in SPTF calculation will be this ladder and then the bubble. And we also have used that exact diagonalization solver, where the H that is the total Hamiltonian can be represented in terms of this impurity, bath and hybridization, and then we first calculate the lattice Green's function here, and then the hybridization function is calculated from this lattice Green's function. And for the exact diagonalization solver we discretize the bath and then calculate this hybridization parameter, and then the epsilon I is the bath eigenvalue, and from there we calculate the self energy. So these are the basic mechanisms which we will be using. And then we calculate the dynamical magnetism, by which we calculate these inter-site exchanges. LCAG is a general formulation which we use from where there is a classical Heisenberg model you write, and then you tilt your spin a little bit around your equilibrium value, and then in the LCAG limit you can write down that Hamiltonian in terms of this J, Ij and alpha beta parameter. So that is a tensorial exchange, which from this tensor value you can calculate the dm parameter, the isotropic Heisenberg and also the anisotropic Heisenberg values. And the atomistic spin dynamics we do, and by after calculating this Jij, Dij and then gamma ij and also the anisotropy, we actually feed it into a LLG equation. There is a two-step process where we initialize the system by a Hilbert Monte Carlo and then solve that LLG by using atomistic spin dynamics. And we have also used this DFT plus DMFT plus MLFT calculation, that is for the cold reverse spectral properties. So there we actually see that our that the 2p level will, the 2p electrons are going to the 3d electrons, so the 2p levels are having a core hole, and that actually modifies your basis set so that your 2p is treated as the valence level, and then we solve a single impurity Anderson model, and in a similar way like this exact diagonalization, we discretize the continuous hybridization function, and the resulting bath states are used in the similar way as the exact diagonalization scheme. So this is the multiplet ligand field theory, DFT plus DMFT plus multiplet ligand field theory, by which we calculate the XAS and XPS intensities, and which I will be showing. So now I am coming to the application to the realistic systems, where we have studied two quasi 2D system. One of them is the chiral magnet, which is Fe4GeTe2. Why I am telling it as a quasi 2D system, you will be knowing slightly afterwards, but as you can see that this one of this layer is actually composed of multiple layers. So this is just encapsulated by tellurium, and then there are iron 1 levels, and then there are iron 2, and then in between are the germanium stuffs. And then this system is having a rhombohedral space group. System is having multiple phase transition near room temperature Tc, and there is a spin reorientation transition and also magnon-phonon coupling present in this system. And there is a quasi 2D Mott insulating series, the next one we will be doing, where we have done a theory plus experimental study, which is a trigonal space group. So this is Mott insulator both in 2D and 3D, and it is also having a low temperature antiferromagnetic order. So the conventional 2D magnetic system, so if you look at it, then usually the magnetic layer is encapsulated within the non-magnetic layer. So howsoever large is the in-plane interaction, if you cannot get an out-of-plane strong interaction, then your Tc will not increase. So that has actually motivated this Korean group to increase means actually they have combined the two structural motifs. So one is GeTe2, another is BCC iron. So they have actually increased the interplane interaction between the irons, so that there are multiple layers of iron. So this is in between actually my the transferring to the data there that has reduce the figure quality. So, but this is a Fe4GeTe2, which is an interesting system, the most interesting system here within this 3 series system. So that we will be discussing here. But in the process of increasing that number of iron within along the interplane direction, that what happened here, that system has become a quasi 2D system, and there are complex site dependent magnetism present within the system, and then this system is also becoming a non-stoichiometric system experimentally. But here whatever we will be showing, we have seen a totally stoichiometric system. So as I have told, this Fe4GeTe2, it is having multiple phase transitions. So if you look at the M versus T measurement, then you will be seeing that there is a ferromagnetic to paramagnetic second order transition at around 270 Kelvin, and then there is a spin reorientation transition, which is a first order transition, which is around 100 Kelvin, and magnetoresistance measurement that also show strange electronic transition where the magnetoresistance actually becoming from positive to negative, there is a transfer of the magnetoresistance, and there is a change from the quadratic to a linear temperature dependence. So what we will be showing here, that how we can explain these phase transformations. So as I have told that magnetoresistance, that there are various, if there is a positive magnetoresistance type, so there is a T square dependence. So there are various kind of quasi-particle interaction like electron, magnon and magnon phonon dependences are there. And then within TQ to TSRT, so that is at the spin reorientation temperature, there is a negative MR, that is magnetoresistance, and there is a mixed T plus T square dependence. So all these kind of these electron, magnon and magnon phonon will be present here also, and but after T is crossing TSRT, there is a linear T dependence is there, and there only electron phonon is interesting. So in our investigation, we will be looking at the electronic properties and then the exchange properties, and then we will be looking at the intersite exchange interaction and the dynamical magnetism, and also the core level spectral properties. This result was published recently, and I will start with the electronic properties. I have mimicked the spin reorientation transition in two conditions where we have taken a, since these are all DFT plus DMFT calculation, temperature is my parameter, one of my parameters. So now we have taken T 78 Kelvin, which is less than T SRT, and here the magnetization is along Z axis. In condition 2, we are having T is 150 Kelvin and magnetization is along X axis, so which is greater than T SRT. And if you look at these the band structures here, then definitely there are quasi-particle interaction region, and then there are lower Hubbard and the upper Hubbard band. You can see that these are the lifetime things. So wherever the lifetimes are finite for the quasi-particle, you will get a band structure kind of things, and otherwise it will be a upper Hubbard or lower Hubbard band with a large smearing. And if you analyze this in condition 1 and condition 2, so there are 6 symmetry operations which are available in condition 1, and condition 2, depending upon its application of the field direction, so there are 4 symmetry operations available. So that means that in condition 2, system is becoming less symmetric. And so if you are looking at these spectral functions, so then you can see here there are 2 regions here interesting. So where one is around this plus 0.3 and minus 0.3, and then around this 0. So there are electronic footprints of this SRT, that means the spin reorientation transition, which shows that if you are increasing your temperature around gamma, these bands are actually shifted downwards in the next one. So you can see here that that there is a opening of a pseudo gap of the order of 0.2 electron volt here, and then there are linearly dispersive Dirac-like crossings around within that plus minus 0.3 electron volt of that Fermi energy. But definitely you can say that plus minus 0.3 electron volt will not be accessible, but usually in experiment people have seen that this anomalous Hall effect, and then those are connected with some Dirac crossings. All the experimental samples are usually non-stoichiometric samples. So for non-stoichiometric samples, definitely these band crossings are accessible. And when we have looked at this 2-dimensional Fermi surface, you can see that side projected Fermi surfaces are very different for with temperature and also with field direction, and for Fe1 and Fe2. There are a lot of more details which I do not have much time, but what I can say that around gamma point, you can see that with increasing temperature, that footprint of that pseudo gap opening, that is there. That pseudo gap is opening, and then that's why this electron smearing that had gone, and that has resulted into a kind of hole pocket here. And So what we have also calculated the orbital and spin projected effective masses, which has shown that they are all in the weakly correlated limit, and magnetic moment clearly shows that there are two types of Fe1 and Fe2, and then orbital moments are, we have also compared this with the measurement. So people have actually next is the DFT plus DMFT plus MLFT to calculate the core level spectral properties, and there we have matched our calculated spectra with the experimental spectra which was there in this publication. Definitely in experiment we do not have any Fe1 on Fe2, so that's why it will be smeared out and it is an average thing, but our theoretical spectra is having Fe1 and Fe2 very different. Not very different, but there are multiple features which are different. So next one is that we have calculated the DFT plus DMFT plus LKAG mechanism to calculate the anisotropic and antisymmetric exchanges. So here that DFT plus DMFT plus LKAG we have calculated for site projected pairwise interactions. You can see that Fe1 and Fe2 interaction, both of them are first nearest neighbor is antiferromagnetic, but Fe1, Fe2 if you look at it, then it is ferromagnetic. More important thing is that DM interactions are very high in these systems, and also pseudo dipolar exchanges, those are also very high. And if you are looking at the RKKY scaling, then for all three of the exchange interactions, that Fe1, Fe2, Fe2 and all Fe1, Fe2 interaction, all of them are having RKKY type of exchange behavior. And the last one is our spin dynamical studies, where we have seen the dynamical structure factors. We have plotted it with temperature and have shown here that there are multiple Q minimas present within this system, and that anisotropy between these multiple Q minima that increases, that actually decreases with temperature. And magnetothermal phase diagrams was also calculated for this system, so where we are varying our field from 0 to 5 Tesla and 0 to 50 degree, and we have shown here that various kind of complex magnetism or magnetic spiral arrangements are there. And what most important thing is that between 30 to 35 there is a change of this magnetic spiral arrangement from ordered spiral to disordered spiral, which has its impact on these magnon spectra along SZ direction. You can see that between 30 to 35 your all degenerate bands are becoming all degenerate bands were actually non-degenerate from 35, between 35 to 30. So these were actually showing that there is an impact of this randomness present here in this system, and then that mode degeneracy of the magnon that reduces the number of available magnon states, and that can lead to a crossover of this positive to negative magnetoresistance. And so I am not reading out the conclusion. The only thing is that we have studied a linearly dispersive band crossing and opening of a pseudo gap by studying this DFT plus DMFT plus SOC. Then DFT plus DMFT plus MLFT has shown a good agreement with the experimental data, and RKKY like oscillations were present, and then the magnetothermal whatever phase transitions were there, we could explain it by our calculations. So next one is our how much time I am having?
You have 7 minutes.
7 minutes. I will try to complete. And so this is our next system is a quasi 2D Mott insulator series, which is a XOH Hall02, where we have shown here. Then in usually the strongly correlated 3D system, there is a tug of war between this U and W. U is the Coulomb correlation, W is the bandwidth, and that U and W that tug of war and is unknown for the 2D limit. So U2D is will be different because of different screening mechanism, and W2D will be different because of the smaller coordination number. And that Mott insulator they are in the U much greater than W limit, and you can also get Hund metal or heavy fermionic system, which are various types of strongly correlated system in 3D. But for 2D whatever happens, it is not known. So Mott insulator, as I have told you, that it is in the U greater than W limit, which were actually first seen by Deboer and Varve, where they have seen that in a partially filled 3D transition metal oxide, that electron counting from simple band calculation that should predict a metallic state, but it is actually a low conductivity. It actually displays in experimentally that very low conductivity. And then that has actually motivated Neville Mott and Rudolf Peierls to write a discussion of this paper, and then they have also predicted the role of strong correlation in narrowband 3D system in this seminal article by Mott, and which actually paved the way of Anderson impurity model in 1967. So Mottness in 2D is not very common, only a few handful of examples of 2D Mott insulators are there. So what we are predicting that this system is actually a Mott insulator from in the 2D and 3D limit, and these are very old mineral systems. Nickel hydroxides are from theophrastite, and then this is kaolinite, cobalt hydroxide. And so we did is a brucite structure, which is a beta phase, that is a trigonal symmetric phase, and then you can see here that these are distorted octahedras are present here, which actually leads to a degeneracy lifting between these XY and XZ and YZ levels. So there is a gap between these two, and so we have done a magnetic phase. Phases are studied by DFT plus U, and then since the DFT plus DMFT plus ED with ED solver, we have studied the paramagnetic phase, since the Mott phase that does not have anything to do with the magnetism. So this is a typical example of a quasi 2D system, because in addition to the van der Waals interaction between the layers, there are also hydrogen bonding present here, and we have calculated the exfoliation energies, which shows that these exfoliation energies are very much close to the natural 2D materials like graphene or transition metal dichalcogenides. And so DFT plus U, you can see that it is these are all antiferromagnetic insulator, where nickel hydroxide is a type antiferromagnet, cobalt hydroxide C type antiferromagnet, and monolayers are only in plain antiferromagnetic states. So DFT plus DMFT plus ED, that also shows a that also shows a insulating behavior, which is around 2. So that is a more accurate calculation, where you can actually get the splitting of the S2D levels and then the D2D levels. Those splittings are also calculated and matched with the optical calculation. And what we have obtained, that we calculated the self energy and correlated it with the Mottness, because you can see that, look at the self energy and can see that there are occurrence of distinct poles in the real frequency axis, so which are of the order of 1 upon omega minus c. So this is a typical example of Mott insulating signature, where this is a hallmark of having being a Mott insulator. So we have more details here, which I do not have much time to say here. So but from first principles, as we have shown that this is a Mott insulator under antiferromagnetic insulating state, and then those are both bulk 3D and 2D form, it will be a Mott insulator. Next is we have prepared some nanocrystalline samples by hydrothermal synthesis. We have shown these are the nickel hydroxides are more like nanoflake, cobalt hydroxides are like nanogranules, and TM has shown us that these are having kind of flaky behavior, and definitely 6-fold symmetries are present here, and optical absorbance, and then from the tau plot we have calculated the DD and SD splitting and matched with the DFT plus DMFT, which has given us a wonderful agreement. And vibrational properties, definitely the calculated Raman active modes and then the experimental Raman active mode, that matches very nicely, and we are having a nice in plane and out of plane distribution of these vibrations here, which actually proves that these are all 2D system. And then the magnetic properties are calculated magnetic properties has shown this antiferromagnetic behavior, and there are DM and PD interactions for monolayer, not for the bulk layers, and then actually if you look at the these SQ omega plots, that means the spin-spin correlation plots, and then the spiral structure which is aligned along the z direction. This is actually a spin spirals present within the system for both monolayer and bulk. And magnetization, when we have experimentally have seen that there is a experimental transition, antiferromagnetic transition, which matches very nicely with our calculated experimental value. In nickel hydroxide we are getting around 20 to 25 Kelvin, which is matching with our experiment. And then since we are having a nanocrystalline sample, there is some frequency measurements were done, and then there is a glassy behavior present. Because of that, this FC and ZFC, that bifurcation that occurs here. And then there are core level spectroscopy we have done, and then that has shown the clear demonstration of multi-configuration effects, because this L3, L2, that ratio, peak intensity ratio is to around more than 2:1. And there are multiplet features present. So the experiment and theory matches very nicely here. And so our conclusion from theory and experiment, that has shown that overall this consolidated investigation that shows that TMOH Hall2 series, that is actually both its 2D and 3D counterparts, it is having a an antiferromagnetic insulating behavior, and it is one of the very rare classes where the 3D Mott insulating behavior extrapolates into 2D. And here are the students who have done the who have participated in this calculation and experiment. Annesha has done some of this theoretical calculation. Nitesh is has done the experimental things, and this is my Noor has done some of the theoretical calculation. Nastaran has taken part in the this spin dynamical calculation. Annesha is present here. She will be presenting her poster on spin fluctuation mediated superconductivity in iron chalcogenide series. I will request everybody to go and ask her many questions. And I also acknowledge my collaborators from Uppsala and Chalmar University. So Ule, Patrick, Anna, Manuel, and Tapoti, and Eva from Chalmar University. And also I acknowledge the funding from Newton Alice Wallenberg Foundation, and then BRC, Uppsala, Light Matter, and computation from BRC Supercomputing Facility, and also from NICE and SUPR. So, and at the end, I thank you all for your kind.
Thanks for the presentation. So now it is open to ask questions.
Yeah, thank you. Nice talk. Ma'am, this DFT, we know altermagnetic is so can DFT prove the altermagnetic like spin splitting or any inside features?
Yeah, definitely it can. So one has to actually. So altermagnet means, are you telling me that it is along SZ and SZ up, SZ down, or it is a non-collinear altermagnet? So that is the question. So if it is SZ up and SZ down, so then it will be far more easier to do. So one has to look at the splitting at various directions, and then has to see that how it can be calculated. So it is there are many altermagnetic experts here sitting here. So you can ask them, they will be presenting their calculation.
Yeah, but we read papers, so they claim the altermagnetic from DFT. So then I understand.
Yeah, it can be done. It can be done, definitely.
Okay, thank you.
Mm-hmm.
Any more questions?
Okay, I can. So, for the first system, you are defining is 2D system, but the magnetic ordering is very high, close to room temperature.
Yeah, that's why I'm telling that quasi 2D.
Yeah. So
Actually,
just I want to know this. What is the interplanar X interaction by in planes? What is the ratio between them?
yeah, that way, if you look at just that one, as I have shown here in my, sorry, the first slide actually. Yeah, here. So these guys, they have actually tried to make it more number of iron layers within one layer of this material. So that has actually, if you look at this layer, so one layer is having many iron layers. So 4 iron layers are
that's
there.
fine, but
So
the
this
next-
here to there, that exchange is actually much, at least one order of magnitude less than this one. But this exchange itself, that this Fe1 to Fe2 exchange is very high. So that's why somehow within this quasi 2D nature, also they sustain that high temperature.
Then above this 3D or magnetic ordering temperature, have you seen any 2D effect? Because it is within the plane,
because-
excitation is strong, so that should show some kind of correlation within the plane.
So within plane means I am looking at this. Mostly the exchanges are very important within this one such stack. So
Yeah.
this one stack to next stack, that is one order of magnitude difference is there. So that's why when you are looking at this thing, so definitely quasi 2D behavior is there. So but from here to then the next level. So then and also these exchanges are very complex here. These are not the regular ferromagnetic exchanges. So
not
if you look at it,
artificial,
it is not not a very good in that out of plane collinear ferromagnet. So as I have shown earlier that afterwards you
My
can,
second question is on that you have found many like spiral order structure.
yeah.
So is it due to the RKK interaction or it is within the Heisenberg model you are getting?
Yeah, within the no, there is no contradiction between this RKKY and Heisenberg, because RKKY mostly look at this Jij thing, and then if you look at this here, so you have to just do that Jij and then this is a scaling. But if you plot that with respect to Rij by A and get a kind of this fluctuating behavior, the plus minus, then it is an RKKY that is almost known. So that happens because of that localized magnetic moments, they interact with that intersite, whatever that delocalized conduction electron, that's why it happens.
The spiral ordering, whether it is a result of long range interaction or simply the nearest
No,
neighbor
I would say it is a long range interaction. This is a long range interaction, definitely, because if you look at the spin correlation, so you get a magnon spectra which is surviving up to this 150 Kelvin. So it is a magnon is surviving up to 150 Kelvin. So it is a long range interaction. The spirals, although the very ordered spirals are present below 50 Kelvin only. So after 50 Kelvin, spirals are becoming very long range. So
almost collinear.
yeah, not collinear I would say, but these are in plane spirals only. Mostly that Fe2, what we have observed is Fe2 is more planar spiral, and since it is stacked within the two Fe1 layers. If you look at this thing, yeah, this inside layer is Fe2, so and outside is Fe1. So outside Fe1s there are more out of plane spins, and in plane. So if you look at this Fe2, that is mostly in plane. So
If anyone has done the Newton diffraction to get the structure on this one?
you have to get such big crystal, right?
I mean powder also can do it around 2-3
If you anybody no
I'm
no,
just
there is
asking whether
there
any
is no
difference
neutron diffraction. That will be very good if you
Yeah.
can do it. I'm just telling you that get a big crystals from somewhere and do it. That will be a very nice, very nice proof of
It's like chromium tellurium, no?
chromium tellurium
That
is
also
also.
shows very like local
Local
chiral
kind,
structure
yeah,
and
yeah,
then
yeah.
global
Yeah,
ferromagnetic kind
it
of
will be
structure.
very nice to have. Yeah,
Chirality.
there.
Yeah.
Very nice talk, man.
Thank you.
Like this is RKY type oxidation, then it is RKY depend on R also. Is there any data that correlate with the R and the magnitude of the oxidation here in your data?
No, I have not seen with R. You are telling.
The distance, yeah, distance between two movements.
Yeah. Here. So with R, you are this you are telling, right? That these are my exchanges plotted with respect to R.
Okay.
So this is Ri by A. So what he was telling, no, that in plane these are all wherever it is very sizable. So there basically it is all within that quasi to this stack, and when it is going beyond that, it is becoming very small. And also there is a very significant amount of DM interaction here, very significant. Actually, if you look at this J by DM ratio, the DM by J ratio actually, that is around 1. For some, yeah, yeah, that is giving rise to chirality.
Maybe a quick question.
Thank you, ma'am, for the talk. As we saw in your lecture, we are discussing about the spin orientation at the particular temperature. I'm just curious, is there any use or practical application for the spin reorientation at the particular temperature, like in plane or out of plane, anisotropic thing?
Yeah, I do not know that whether anybody has done any application of this SRT, means that is spin reorientation transition, but definitely it can be applied that if you wanted to have some, since these are all having this chirality present here, so basically if your magnetic field is gradually changing its direction, then your whole texture will change, and that will have some impact on it, your spin orbit torque and everything. So that way, that spin orbit torque devices should have some impact, that from in out of plane to in plane, if I am gradually changing my magnetic field and then measuring the spin orbit torque, that should give a signature of this whole thing at spin reorientation transition. And also there was a recent measurement done by Otin and their group. So they have shown that there is this magnon-phonon coupling. So magnon-phonon coupling, there is actually a peak at the spin reorientation temperature. But that definitely that they have calculated this magnon-phonon as my earlier one of the, they have done it under harmonic approximation, and then from very crude approximation of dividing that whole lambda SISJ divided by that saturation magnetization, that kind of crude approximations they have made, but still there was a kind of indication that there is that spin that phonon coupling that has a peak at SRT, that spin reorientation transition. Yeah, thank you.
Okay, so let us thank the speaker again.
Yeah.